In this presentation, we'll focus on linear and angular kinematics. So kinematics is the study of motion, regardless of forces causing that motion. And we are going to talk about linear and angular kinematics. Let's go through it. In a previous presentation, I described the three types of motion: linear, angular, and general. Linear is all points of an object travel the same distance, either in a straight line, rectilinear, or in a curved line, curvilinear. And angular motion is about an axis. And general motion is a combination of linear and angular motion. And as I've talked about before, is when we are studying human movements, it's almost always general motion. There can be some specific movements that we can say are linear movements or specific movements that are angular, but mostly the types of movements that we're interested in, throwing a ball, kicking a ball, swimming, what have you, is going to be general motion. And what we do in our kinematic analysis is we will break that analysis, that movement, into different components and then study those components, those smaller components, and then bring those components back together to understand the general motion. So what we'll do typically is do a linear analysis, then we'll do an angular analysis, and then we pull those together to understand general movement. In our linear analysis, we'll even break that down even further, and we'll look at the linear movement in only the x direction, or the linear movement in only the y dimension, or only in the z dimension. So you'll often hear me talk about doing a linear analysis in one dimension, one space dimension, and then time. And so that taking that path, going down that line of thought, allows us to really zero in on one aspect of the movement, try to understand that aspect of the movement, and then go forward and combine that with other components of the movement. And same thing, we're doing an angular analysis, and we'll look mostly at joint angular movement or movement of a segment by itself. So a segment being an arm, a forearm, thigh, leg, a joint being a knee, hip, elbow, what have you. And we take those different movements, or those rotations, and we try to understand them individually and then combine that with other information to understand general motion. All right, so that's sort of big picture of where we're going here. If we look at this as a semester and trying to understand kinematics, the first thing we do is we spend a lot of time on understanding linear kinematics, and we do a lot of description of linear motion. And then we switch gears and we do angular kinematics, and we really focus in on angular motion. And what we see is that the concepts are the same in that we are trying to understand position, velocity, and acceleration. It's just some of the terms are different, some of the symbols are different based upon whether we're in the linear world or the angular world. And we may be talking about linear position, linear velocity, linear acceleration, or we may be talking about angular position, angular velocity, and angular acceleration. So the concepts are the same. It's just the type of movement that we're talking about leads to different symbols to represent these different concepts: position, velocity, and acceleration. All right, so position, let's go with linear kinematic. And now we're going to talk about the linear kinematic parameters, and we're going to talk about position, velocity, and acceleration. Well, position is location of a point or of an object in space at some moment in time. And what we're interested in is movement. So we're going to track that object and how it changes space, how it changes its position in space over some time period. And there's two terms that we use when we start talking about the change in location or change in position of an object: distance and displacement. Okay? Distance is defined as the total change in position. This is the odometer in your car, or your odometer on your bike if you have one. This is how far you've changed position regardless of what direction you're headed in. If I drive from home to campus, that's 10.5 miles. That's how far I traveled in distance. It doesn't have a direction associated with it. The units of distance are units of length, meters, feet, miles, yards, inches, centimeters, whatever it is. What's important, and I'm going to describe this a little bit more, this is a scalar. A scalar is any parameter that's represented by magnitude only. Distance is a scalar. It only is to tell you how far we've traveled in distance. I only need to give you magnitude of that distance. 10 miles, 26 miles, 50 miles, what have you. Displacement is still under our position parameter, but displacement represents a straight line distance between 2 points. The equation we'll use, it depends on which book we picked up, but it could be, in this case I have P here, change in P equals PF minus PI, final position minus initial position, okay? Sometimes I use S, sometimes L, sometimes X, sometimes Y, sometimes Z. The symbol here will change, but the symbol will represent the location in space of an object, and the delta sign represents a change in position, and we always will do final minus initial, always. The units are still units of length. In fact, the same units as distance, meters, feet, miles, yards, inches, centimeters, what have you. But displacement is a vector, and a vector is any parameter that's represented by two things, magnitude and direction. All right, so vector, we have to describe not only how much of a change in position this object had, but in what direction that change in position occurred. So it becomes a little bit more specific. Now, if you're in a physics class, your physics instructor might actually say distance is the magnitude of the displacement vector. In general, that's okay when we are dealing with small time periods that we're looking at. I'll show you some examples where distance and displacement are not the same in magnitude, and that's only because our time period is really big that we're actually looking at. But if I'm hanging out with my physics friends, physicist friends, that's okay. We can understand each other when we start talking about distance and displacement. Displacement's a vector. It's going to be represented by magnitude and direction. I'll go in that in more detail in subsequent presentations. Distances are scalars represented by magnitude only, no direction associated with them. All right. So a little bit more on vectors and scalars. It's just repeating what I said. Vectors are parameters that are represented by two things, magnitude and direction. Scalars are parameters represented by magnitude only. So as we go through this course and you hear the introduction of different terms, and you hear, oh, this is a scalar, or this is a vector, that's important to know. All right, so you're going to want to know when a parameter is a scalar or when it's a vector. It's important to know because the math for scalars is just math that we do every day. For example, if I ran 5 miles today and I run 3 miles tomorrow, my total mileage would be 8 miles. Scalar math, okay, nothing to it. However, when we do math with vectors, we now need to account for not only the magnitude, but also the direction. So if I ran 5 miles north, stayed somewhere, and then I ran 3 miles south, my displacement from my origin, my original starting place, would only be 2 miles, okay? Because it's final minus initial position. I'll go through more examples as we do this. But the key is, if a parameter is a vector, I need your radar to go on and say, math is different for vectors than it is for scalars. Or you have to account for the direction of the parameter when you are doing your math. So there's just a little finer rules when we're dealing with math of vectors. Scalars, scalar math. Direction's not doesn't matter. Run 5 miles, 3 miles, add them up, it's 8 miles. All right, a little bit more on position. There's just a schematic of distance versus displacement. So here I've got this object at this location and then in this location. And I've got in essence, the same object. I've got different colors just so that we can distinguish them from each other here. This is the same object moving to the same place. If this object went from here and traveled this path, to measure the distance, I'd have to pull out my measuring stick and measure the total length of this path. That's distance. Displacement simply takes a straight line distance from the final position to from the original position to the final position. That straight line distance, that length of that, is displacement. The length of this line is distance, so total change in position. And that's how we'll distinguish this. Again, if you're in a physics class, you may shrink that delta t down to being something really short, where your magnitude of displacement vector ends up being distance. But in our world, we actually have many movements that occur over long periods of time, and we need to either decide to use distance or displacement when we are discussing the total change in position. Here's an example. This is a famous swim down at Alcatraz. Here's Alcatraz Island. In this swim, you get on a ferry, a boat, and it takes you out to Alcatraz Island. And then they blow a horn, and everyone jumps off the boat and swims to the shore. All right, sort of an iconic swim. It's wavy. You've got currents in here. I guess there's sharks in here. I don't know. But you've got to navigate your swim from where you drop off the boat, where you jump off the boat, to where the beach is. Now, if you're really good in swimming in open water, you can swim a nice straight line to the finish. However, this body of water is very notorious for currents and sometimes very unpredictable, and you're getting hit by waves. And so in this case, this is me actually swimming. I wore a GPS watch to tell me my position over the swim, and you can see how I actually got drifted off here to one side. Then I had to make a correction and come back in. That length is my distance. This yellow line represents the displacement. This is the advertised length of the swim. They say, I can't remember what it is. I think it's a 1.2 mile swim, but it's not 1.2 miles for me. It was longer. Maybe it's 1.4 miles, maybe 1.5. All right, so even these little squiggly lines in here, I'm not swimming a straight line. I'm getting tossed by some waves. It may be more important to know the distance that I swam when I'm analyzing the swimming motion. However, when we start talking with other swimmers, we all swam 1.2 miles because that was the displacement that was measured for this course. And whether you swam further or longer, it doesn't matter. You've got, the shortest path is this straight line right here, and you want to try to do that as much as possible. Oh, and you can see, I meant to mention, here's our reference frame. And again, it doesn't matter where we put this origin. This would be a global reference frame, and it does not move, and we can quantify that position relative to this reference frame. All right, let's keep moving. So now some other kinematic parameters. So position is what I just went through. Now we've got velocity, and velocity tells us how fast we're changing position. So it's time rate of change of position. Technically, it's time rate of change of displacement. I'll often get lazy and I'll say rate of change of position, but technically velocity is the rate of change of displacement. The equation, delta P over delta T, so final position minus initial position in the numerator, the top number, final time minus initial time in the denominator, the bottom number. That's how we calculate velocity. The units of velocity are any units of length over any units of time. Meters per second, feet per second, yards per minute, miles per hour, kilometers per hour, kilometers per second, what have you. Any units of length over any units of time. Velocity is a vector, all right? So remember, your math radar is going off, and you're going to say, okay, if I have velocity, I have to account for not only the magnitude of velocity, but the direction of velocity. And we'll go through this course coming up with ways to manage the math of that direction aspect of this vector. But for now, it's important to recognize velocity is a vector. It's rate of change of displacement, how fast we're changing position. The other parameter that's closely associated with velocity is speed. You've got a speedometer in your car, and that tells you how fast you're going, 30 miles per hour, 50 miles per hour, what have you. Speed is the time rate of change of distance. Okay, so not displacement, but distance. The units are the exact same units as velocity units, any units of length over any units of time. Meters per second, feet per second, miles per hour, kilometers per minute, any units of length over any units of time. Speed is special in that it's a scalar. It's represented by magnitude only. If you're looking at your speedometer in the car, that's what your speed is. That's telling you how fast you're changing position from a distance perspective. Now, with my physics friends, if I'm hanging out and having coffee with them, they will often say the magnitude of the velocity vector is speed. And again, that works as long as our delta t is a small delta t. And I'll go through this in more detail as we go through other presentations. But for our course, and often in kinesiology, we will often distinguish between speed and velocity because sometimes our delta t's are very large. So for example, I go back up here to this swim, it's the same delta t for each of these lines, but my velocity will be faster for this yellow line versus the red line, okay? Because distance and displacement are different magnitudes in that example. All right, so speed is a scalar, magnitude only. Velocity is a vector, magnitude and direction. Okay, the next kinematic parameter, the third one and final one, is acceleration, time rate of change of velocity. It tells us how fast velocity is changing. This is the tough one, and we'll spend a lot of time trying to understand and make sure we're understanding what acceleration is. But acceleration is simply telling you how fast velocity is changing. The equation is delta v, final velocity minus initial velocity in the numerator, divided by delta t, final time minus initial time in the denominator. That's our acceleration. The units are any units of velocity over any units of time. So for example, meters per second, which we can also say meters per second squared. We can do that math separate. Feet per second, miles per hour per second. If you are a car buff, you probably know this as an acceleration rating of a car engine is the mile per hour per second rating, which is an acceleration rating of a car. Kilometers per hour per second, miles per hour per minute, it doesn't matter. Any units of velocity over any units of time. Acceleration is a vector. It's represented by magnitude and direction. And we are going to spend a lot of time understanding this vector because it's actually really quite important to understanding human movement or movement in general, because I'm sure you know or have heard Newton's second law, sum of forces equals mass times acceleration. There's the acceleration parameter. We need to understand acceleration to link to our kinetic world. There's no scalar parallel to acceleration. All right, we're only going to deal with acceleration. We do not do time rate of change of speed. We only will do time rate of change of velocity. Okay, so yeah, just acceleration is a vector, magnitude and direction, and we'll spend a lot of time working on understanding that direction parameter. All right, so that's linear. All right, now angular kinematics. Position, velocity, acceleration, angular position, angular velocity, angular acceleration. Those are the same parameters. And what we're going to learn is that the relationship between these parameters, the math behind the parameters, is exactly the same, whether we're in the linear world or the angular world. All that's different are some of the symbols that we're going to use and the concept of the movement that we're actually trying to study. In this case, I've got my laboratory reference frame here. I've got this segment in an initial position and then in a final position. It's green here and it's red over here. And it rotates, so angular motion, rotational motion about this axis. All right, let's go through this. And the first thing we need to do is identify angular position. I've got another video on angular position, but for right now, what I'm doing is I'm drawing out this reference line to the right, and I'm going to take the angle between this reference line and my segment of interest. In that initial position, I'm going to describe using Angular units 170 degrees. The angle between this reference line, which is parallel to the x-axis, and the segment of interest is 170 degrees. That's my initial position. My final position, I'm going to use that same reference line. I'm going to go from that reference line to my segment of interest. The final position is 45 degrees. All right, that's just telling me the angle between my reference line and the segment in space. So angular displacement is just final minus initial position. It's the analog to straight line distance between the final and the initial position. In this case, this is the final position, this is the initial position, and all we do is go from here to here, and we get that angle. In this case, it's negative 125. Final position is 45 degrees, initial position is 70 degrees, so final minus initial is negative 125. Angular displacement is a vector. It's represented by magnitude and direction. The magnitude is the 125 degrees. The direction is this negative sign. All that direction is telling us is which way we're seeing rotation happen from a displacement perspective. So negative sign simply means the rotation was clockwise. The positive negative sign simply indicates direction of rotation. And we'll go through this in deeper, we'll do a deeper dive on this in subsequent presentations. All right. Typically, negative signs are not used for angular distance. We would just say it's 125 degrees from this position to this position. However, if we deal with something with multiple rotations, like somersaulting, and this segment rotates several times, then we have to account for that each rotation in our angular distance parameter. So if we go around once, that's 360 degrees plus this final movement from this position to this position. So angular distance can be larger than 360 degrees. Angular displacement will always be smaller than 360 degrees. 360 degrees is one complete rotation. Okay, so that's angular position, angular displacement, final straight line rotation from initial position to final position of an object rotating. Angular distance, it accounts for multiple rotations. Angular velocity is the next kinematic parameter, time rate of change of angular displacement, and we use omega equals delta theta over delta t. Final angular position minus initial angular position over final time minus initial time. The units are any units of angular displacement over any units of time. Oh, I should have gone back up. I don't know why I'm missing that in my slide up there. But units for angular displacement are degrees, radians, or revolutions. So units for angular velocity are radians per second, degrees per second, revolutions per minute, any units of angular displacement over any units of time. Angular velocity is a vector, has magnitude and direction, and that direction is going to be the positive or negative sign in our math calculation. Angular speed is time rate of change of angular distance. We don't have to deal with direction. We're dealing with magnitude only. The units are the exact same units as angular velocity, radians per second, degrees per second, revolutions per minute. Any units of angular distance over any units of time. Angular speed is a scalar. It's represented by magnitude only. All right, our final angular parameter is angular acceleration. Angular acceleration is how fast angular velocity is changing. Time rate of change of angular velocity. In this case, we use the symbol alpha equals delta omega, change in angular velocity, over delta t, change in time period. Final angular velocity minus initial angular velocity divided by the final time minus initial time. The units are any units of angular velocity over any units of time. Angular velocity, degrees per second, radians per second, radians per minute per second, any units of angular velocity over any units of time. Angular acceleration is a vector. So again, your math radar needs to go off, and angular acceleration will have a magnitude and a direction associated with it. We need to account for both of those when we are doing our math for angular acceleration. All right, summary of this portion. The kinematic parameters are position, velocity, and acceleration. In the linear world, we have linear distance and linear displacement. Linear distance, total change in position. Units are any units of length. Displacement is a straight line distance between 2 points. Same units, any units of length. Distance is a scalar, displacement is a vector. Velocity is time rate of change of displacement, how fast position is changing from a displacement perspective. It's a vector. Speed is the time rate of change of distance. It's a scalar. Both share the same units, any units of length over any units of time. Velocity is the vector, magnitude and direction, and speed is the scalar, magnitude only. And then we have linear acceleration, which is time rate of change of velocity. We will not do time rate of change of speed. We will only do time rate of change of velocity. So delta V over delta T, final velocity minus initial velocity divided by the change in time. Any units of velocity over any units of time, so meters per second, meters per second per minute, feet per minute per second, any units of velocity over any units of time. That's the linear world. In the angular world, we simply say angular position, angular velocity, and angular acceleration. The equations are exactly the same. We just use different symbols. We use theta for angular position. We use omega for angular velocity. And we use alpha for angular acceleration. Angular position from a displacement perspective is a vector. Angular distance is a scalar. Angular velocity is a vector. Angular speed is a scalar. And angular acceleration is a vector. Okay, just nail all those terms. Know your definitions, equations, and units, and that will be helpful as we go forward in this class. All right, thanks so much.